Today we're focusing on cooling the built environment. My name is Maria Cutter, and I'm the Climate and Sustainability Specialist here at CoolSeal. This is our agenda for today. We have two excellent presentations from Karima Salim and Shenyi Liu. So we are very excited to share their excellent work with you guys. So today's webinar is going to be recorded so that it's available to you all afterwards. And we do have everybody set on mute with cameras off. So please, if you will, add your any comments or questions to the chat box, and we'll answer those towards the end at the end of the webinar. And feel free if you have any suggestions or thoughts on future presentations or people that you like to hear from, go ahead and add those to the chat box. So I'll go over a quick review of what we're doing with our sustainability program. We know that extreme heat is a problem. It's getting worse all the time. According to NOAA, in the US alone, over 5,000 records were set or tied in June and July only. And in the UK, globally, over 10,000 records were set. In the UK, they had the hottest summer on record since recording began back in 1884. So one of our key goals is educating and increasing awareness about heat mitigation strategies and the contributions of heat mitigation on climate activity and climate change plans in communities, private sector, public sector, and all across the board. Reflective surfaces are a key strategy to cool the built environment, and a lot of education is needed about that. Even in the cool roof sector, trees, cool pavements especially because it's so new, and cool pavements are roughly where cool roofs were about 10 years ago. So we're trying to advance the knowledge base around that. Part of growing anything is having good collaborations and having a lot of different faces and voices at the table. So that's another thing we're working on, is promoting collaborations across sectors with stakeholders from all kinds of different groups: academia, research, the public sector, local governments, and even private sector as well. So collaborations are key and one of our focus areas. So when it comes to understanding new strategies and innovative approaches for heat mitigation, research is the key. We know that there's research available, there are new research findings available, but there's a lot more that needs to happen to help address the pros and cons of cool surfaces, and it's the right solution in the right place, be it roofs, trees, and pavements. So we want to know when that is the right thing to do in different places. And of course, grow the body of knowledge that will also help address innovation, where we can improve our products, as well as bring costs down. So we know that cost is a barrier, and we want to help assist with funding. We're taking a close look and always watching opportunities. They're coming out of the infrastructure resilience funding. And we're also looking at different grants through the EPA and the government website. So we're trying to provide opportunities and awareness to our stakeholders that help assist with funding. We don't want cost to be a barrier, so that's really important. Okay, well, that's a little summary of our sustainability work. And now I'm pleased to introduce Davis Coleus, who is our Sustainability Director, and he will give an introduction to CoolSeal.
Thanks, Maria. Good afternoon or good morning, everyone, from wherever you're joining us. Wanted to do a quick intro on CoolSeal for those that aren't familiar. Our parent company has been in the asphalt maintenance industry for 40 years, manufacturing products to maintain asphalt surfaces and make them last longer, to improve the lifespan of asphalt and improve on infrastructure. And about 11 years ago, we developed CoolSeal to do everything that a traditional asphalt maintenance product does, from extending the life of the asphalt and protecting the infrastructure, but also to be an urban heat island mitigator. And CoolSeal was born from there. And in the last 10 years, there's been a significant amount of product innovation and development to where we are today, where CoolSeal has been applied in 21 states and 6 countries around the world, multiple millions of square feet, to now where there are multiple programs happening, in municipalities across the globe with CoolSeal, and we're seeing a lot of benefits because of the cooling that are increasing some of our maintenance benefits as well. If anybody is interested offline, we have some really great third-party data. In 2020, Arizona State University conducted the largest cool pavement study to date. Was funded by the City of Phoenix Street Transportation Department, and they studied for a calendar year and found some really great benefits that led them to proceeding to a full program. And now this program has been ongoing for 4 years, and it can continue on annually. And after that first initial year of study in 2020, Arizona State University has continued to monitor the performance over the years to ensure that they're still seeing the benefits from a maintenance and a cooling perspective. And there's been some additional data that's been released recently that has shown that through year 2 and year 3, they're seeing similar data to the first year, so that the product is maintaining its solar effectivity and infrastructure benefits. And that'll be continued to be studied over the years continually. So it's great to see that that has been going on. We've had many new municipality projects take place this year, some new countries for us, and also some new cities. There's also, as some of you may have attended our last webinar, there's some additional research being done from other municipalities, and we're hoping to have some of that data by the end of the year to share. And we're also undertaking our first private development project that's being studied at an extensive level. There's a commercial shopping center in the Phoenix area that we have applied CoolSeal at, where they're comparing our product to traditional seal coat and are looking to identify the benefits from a private market perspective, to identify not only the maintenance benefits, but also some of the cooling benefits that are potentially going to lead to energy savings. That's being studied by Arizona State University Sustainability School, and that's going to be a year-long study as well. So going to be a great way for us to analyze third-party data from a new subset of category, being more of a commercialized shopping center rather than with the municipality, where they're focused on, different things, obviously similar in some aspects, but commercial developments and getting these Fortune 500 companies and private development companies focused on urban heat mitigation is going to be important, because obviously with 40% of the built environment being asphalt, not all of that is maintained by cities. There's also private markets, so getting that involvement, and there's going to be some lead elements to that as well that we'll obviously talk about today. But wanted to say again that thank you for everyone for attending. We've got some more webinars coming. We're hoping to have one in the winter, and we don't have any speakers yet, but I guess I'd say if anybody's interested in speaking, we're obviously open to that. And if you're, maybe recommend some people that you think would be good to speak on some of these urban heat mitigation topics, because we're looking to educate and inform about all things urban heat. So with that, that's a little bit intro to CoolSeal, and I'll toss it back to Maria. I think you're still muted there, Maria.
All right. Thanks, Davis. So it's time to introduce our speakers. Today we have Karima Salim from the U.S. Green Building Council. And Karima, I will note, is a little bit under the weather, so she is still joining us, but with camera off. So Karima is the Associate Director of LEED Standards and has extensive experience in design, project management, green building, and environmental policy. Karima oversees technical development for LEED's sustainable sites and integrative process categories. She manages LEED credit projects and committees and leads initiatives related to resilience and social equity. So please join me in welcoming Karima.
Thank you so much, Maria. I'm going to go ahead and share my screen. It's a pleasure to be here, and again, apologies for being off camera. I hope all of you are staying healthy and masking up where appropriate. COVID is out and about again. Can everyone see my screen? Okay.
Yes.
Awesome, thank you. So, as you heard, my name is Karima Salim. I'm an Associate Director on the LEED Technical Development Team at the USGBC. and I help to manage the sustainable sites category and the committee. This is an infographic I'm going to start with from the APHA, the American Public Health Association, and I like to share this infographic because it shows the multiple ways in which extreme heat impacts your health, including dehydration, heat stroke, aggravated cardiovascular illness, and aggravated respiratory illnesses. The urban heat islands are urbanized areas that experience higher temperatures than surrounding rural areas and less densely developed areas as a result of structures such as buildings, roads, and other infrastructure that reflects the sun's heat more than natural landscapes. Daytime temperatures in urban areas are about 1 to 7 degrees Fahrenheit higher than temperatures in surrounding rural areas, while and nighttime temperatures are about 2 to 5 degrees Fahrenheit higher. Urban heat islands also worsen extreme heat events, such as heat waves, and thus the environment and residents living in heat islands are unfairly subjected to negative impacts, such as the health impacts I mentioned earlier. Higher temperatures in cities are caused by the lack of natural landscapes, such as green spaces, water bodies, and trees that regulate temperatures through evapotranspiration, evaporating surface water, and providing shade, respectively. Urban infrastructure and the way cities are constructed and the materials they're constructed with have a huge impact on how urban microclimates are shaped. And in urban areas, natural landscapes are replaced by low albedo materials, such as pavements and roofing, that absorbs and retains heat during the day and slowly releases it through the evening and nighttime. Also, dimensions and spacing of tightly packed urban spaces impacts wind flow pattern and how solar radiation is absorbed and emitted. And lastly, anthropogenic heat and climate change and the increase in temperatures caused by human activities like vehicles, air conditioning, and heating in buildings and industrial facilities generate and emit waste heat more than rural areas. So these higher temperatures combined with other climate phenomena such as humidity and dew point really have numerous impacts on the urban environment and residents' heat experience. Some environmental impacts of urban heat islands that impact human health are increased air pollution and degrading water quality. So for air pollution, since temperatures are higher in urban heat islands, especially during heat waves, there are higher energy demands for air conditioning and other cooling strategies. So the increased use of electricity leads to more greenhouse gas emissions from fossil fuels, and thus contributes to localized air pollution as well as exacerbating global climate change. Along with air pollution, urban heat islands also deteriorate water quality. One study found that urban streams are hotter on average than streams in forested areas, and that temperatures in urban streams rose over 7 degrees Fahrenheit during small storms due to heated runoff from urban materials. However, as you'll learn later in this presentation, materials can be a part of the solution, and we'll talk about that more in a moment. So urban heat island effect also has devastating consequences on infrastructure and human health. With consistently higher temperatures in urban areas and especially high temperatures during heat waves, building materials like tarmac, concrete, and steel are all affected and deteriorate much faster due to temperature fluctuations. Along with that, power grid failures become more common as energy demand increases. Excuse me. Along with that, power grid failures become more common as energy demand increases due to increased cooling requirements. So according to a study done by the University of New South Wales, there will be a 12% increase in cooling demand in urban heat islands compared to demand under reference rural climate conditions. And this increase in demand leads to power grid failures because the current grid is inadequate to handle the rise. And this is already impacting thousands of urban residents in the US as blackouts nearly doubled from 2015 to 2020. The rolling blackouts in the Northwest US last summer is also another example of or previous summers, is another example of insufficient power grid in increasingly warming areas. UHI's higher daytime temperatures, reduced nighttime cooling, air pollution have severe impacts on human health and comfort, especially for sensitive populations such as older adults, young children, low-income populations, outdoor workers, and those with comprised health like chronic conditions such as asthma, diabetes, and physical or cognitive disabilities. And heat-related illnesses that these populations are susceptible to are general discomfort, respiratory difficulties, heat cramps, heat exhaustion, and non-fatal heat strokes. According to the CDC, over 65,000 people visit emergency rooms for acute health illness each summer. And a Duke University study found that an average of 12,000 premature deaths occurred annually in the US during the last decade, and projected deaths rise to 110,000 annually under a business as usual warming scenario due to climate change. And as climate change worsens, it contributes to and exacerbates UHI in cities by raising overall temperatures, as well as increasing frequency and intensity of extreme heats. And it'll be equivalent, UHI warming will be equivalent to half the warming caused by climate change by 2050. And this is, in turn, will increase islands and their impact on humans and the environment. And since urbanization is also projected to increase from the current 55% to 68% by 2050, more and more urban residents will be vulnerable to these impacts. So because of the urgency and severity of the matter, it's even more important to mitigate the damaging impacts of UHI and do it equitably and with the community at the forefront of the conversation. Low-income communities and communities of color are more likely to face urban heat temperatures and more vulnerable in extreme heat events. And since UHIs disproportionately impact low-income and communities of color, they're an environmental justice and public health issue. This figure 6 here illustrates the correlation between income level and surface temperatures across 4 cities in the US. And the lack of cool materials and as well as green spaces in these communities leads to higher surface temperatures caused by heat absorbing urban materials such as asphalt. So figure 5 shows the lack of tree cover in low income neighborhoods in DC compared to middle income and high income communities. And low-income communities and communities of color are also more susceptible to heat due to the lack of access to cool and safe indoor environments and outdoor environments and civic amenities like cooling centers. So often low-income residents cannot afford effective and efficient air conditioning systems, and they thus rely on community cooling centers, but these centers are few and far apart. Worsening that situation is a lack of access to safe and affordable healthcare in cases of heat-related illness, which causes more fatalities, especially during heat waves. And low-income and marginalized communities are significantly more heat vulnerable, again, because of, and also vulnerable because of historic discriminatory land use policies, lack of investment in these historically marginalized communities, and associated crime safety concerns by residents of the community. Historically, red line communities are much hotter than non-red line neighborhoods because of a lack of investment in their maintenance and upkeep, such as cooling structures, cooling materials, tree canopy, and safe construction materials. Figure 7 shows the difference in average temperature in various neighborhoods. And as you can see, the neighborhoods with a rating of D are much hotter. And out of 108 urban areas studied, nearly all redline areas in these cities had higher temperatures than non-redline areas, some by nearly 13 degrees Fahrenheit. So a little about LEED. LEED, or Leadership in Energy and Environmental Design, is the U.S. Green Building Council's third-party verification system for green buildings at all scales, from private homes to large commercial skyscrapers. And LEED criteria can be applied to a new or existing building and offer 4 rating levels based on points gained for energy, water, waste, materials, transportation, human health, and other categories. It's the most widely used green building rating system in the world, and it's a critical part of addressing climate change and enhancing resilience and supporting more healthy and equitable communities. Here are some credits that are relevant to heat island reduction, and we'll be going through some of these today. These include heat island reduction, heat island mitigation through cool walls, which is a pilot credit, carbon sequestration through plantings, which is also a pilot credit, and then 3 main credits: integrated process, protect or restore habitat, and open space. In the new version of integrated process in version 4.1, there is a health section that is relevant to this topic. And there's also new opportunities with the new LEED version 5, which was just released for O&M at Greenbuild this year in September, which I'll be talking about in a moment. So this first credit in LEED that's leading charge on combating extreme heat is the heat island reduction credit under the sustainable sites category. And the goal of that credit is to minimize inequitable effects on microclimates and human, especially frontline communities and wildlife habitats by reducing heat islands. We recently updated the intent section of that credit to include language inequitable effects at frontline communities in order to explicitly recognize that heat islands are an environmental justice issue and a public health issue, and equity must be a part of the solution for more healthy communities. So to earn 2 points in that credit, projects could choose non-roof or roof measures and use any combination of non-roof and roof measures or parking under cover. So examples of non-roof and roof measures include installing plants to provide shade over paving areas, but also providing reflective paving materials with high solar reflectance values, or using open grid pavement systems on high reflectance roof. Many projects have achieved this credit with an achievement rate of over 80%, and some will be highlighted later in this presentation. Oops, sorry. There's also the pilot credit heat island mitigation with cool walls, authored with the Cool Roof Rating Council, in partnership with the Cool Roof Rating Council. And it's similar for the first credit, but it's more about the process used specifically to reduce heat through cool walls. Cool walls are walls often painted a cooler color than usual to increase the SR, or the solar reflectance value of a building, by allowing it to reflect more of the sun's heat back into the atmosphere instead of absorbing it. And conventional walls reflect about 25% of the sun's heat, whereas cool colored walls are about 40%, and off-white or dull white about 60%, and bright white at about 80% reflectance. So cool walls allow heat to be released from infrastructure that would otherwise hold on to it, and thus reduce the urban heat island effect. They also reduce a building's cooling load, thus saving energy and in turn reducing greenhouse gas emissions. So the requirements for this credit are that at least 75% of the building's gross exterior walls are a cool wall, with specifications about what qualifies as a cool wall and where the cool wall must be located. Our most recent data shows that there are 10 projects registered for the credit, and out of the 10, two projects are currently working towards achieving it for an industrial manufacturing project. The project is using BD&C core and shell to increase SR values and reduce UHI effects. This says 5 projects, but it should be 10. The next pilot credit relevant to urban heat islands is the Assess and Increase On-Site Carbon Sequestration Credit, or the On-Site Carbon Sequestration through Plantings Pilot Credit. It was just recently retitled. And this credit intends to increase awareness and understanding of a site's carbon. The first requirement of this credit is to use the most current version of the iTree planting calculator to assess the amount of carbon sequestered by trees and shrubs on site. Once a baseline is established, the project can increase carbon sequestration by at least 10% compared to the baseline state, or use alternative strategies. And this credit reduces urban heat temperatures by increasing green spaces and vegetation on site that evapotranspires and regulates temperatures. The figure here shows a difference in temperatures between asphalt roads versus trees. And right now, our committees are discussing how to account for carbon sequestration through materials. So stay tuned on that development. A study published in MDPI journals found using GIS and spatial regression models that constructing LEED certified buildings in a 30-meter area could lower the temperature in the surrounding environment by 0.35 degrees Celsius. A LEED Gold or Platinum certified building could lower the temperature by up to 0.48 degrees Celsius, while a Silver or certified status could lower the temperature by 0.26 degrees Celsius. And these small temperature reductions caused by one building, or one LEED building, can be multiplied by certifying more existing and new buildings under the LEED rating system. And the more LEED certified buildings there are in a city, the less urban heat island effect will impact the health of the growing urban population. Case studies undertaken by the Leads for Cities team to tackle urban heat were focused on projects and campaigns in Louisville, Miami Beach, and Cincinnati. In Louisville, which was one of the first large cities to undertake such a large-scale study, they found that parts of Louisville had temperatures of up to 10 degrees Fahrenheit hotter than surrounding areas. Louisville has the fastest growing UHI On average, Louisville was 4.8 degrees Fahrenheit hotter than rural areas from 2004 to 2014. Temperatures in Louisville have been increasing by 0.65 degrees Fahrenheit per decade since 1960. And to improve quality of life and reduce UHI effect, uh, investing in cool and reflective roofs through a Cool Roof rebate program offers $1 per square foot for installing Energy Star rated roof. Property owners installing reflective roofs save 7 to 15% on cooling costs, and 70% of the program's funding goes to vulnerable neighborhoods that were historically redlined in 2017. The Cool Roof Rebate Program has incentivized the installation of over 820,000 square feet of cool roofs. The Green Heart Louisville program tested the effects of heat and greening on health and well-being on residents. And a Parkland Plaza project turned that project, which was an unused city-owned parking lot, into a green space with trees and cool pavements. In Miami Beach, Florida, rising urban heat and other impacts of climate change, such as rising sea levels, saltwater intrusion, and stormwater management, led to the creation of Urban Heat Island Ordinance to address the impact of climate change. The Green Building Ordinance that requires every new construction over 7,000 square feet to be LEED Gold or meet the Living Building Challenge. The Urban Forestry Master Plan that aims to, in Miami Beach, aims to increase urban canopy coverage by 22% by 2040. In Cincinnati, Ohio, disproportionate heat impact on vulnerable populations was found, and it was found using citizen science to collect 10,000 data points over the course of a day. Targeted improvements to vulnerable neighborhoods include, so currently some neighborhoods have over 70% canopy coverage, while historically redlined neighborhoods have less than 10%. So the goal is to improve overall canopy coverage to 40% and also installing indoor and outdoor cooling stations, especially in heat vulnerable neighborhoods. So adding cool pavements by rolling back requirements for parking lots in certain zones is also part of their solution. So these are some great examples of how city-wide these issues are being approached. So what's next? Right now at LEAD, we're discussing how to find solutions to the following, and curious to hear from you and in the audience and the market your ideas on how to tackle these solutions, which includes the following: inequitable disparities in terms of health and extreme heat, the cleaning of roofs, especially green roofs and roofs in which you want to maintain the reflectance, the solar reflectance value, the cost of maintaining green and cool roofs, the lack of education around this topic, and the perception that designing for heat island reduction is overly expensive. And the evolution of LEAD is ongoing in terms of tackling these issues. In June 2022, USGBC published the Future of LEAD report, which established core principles that will drive LEAD version 5 updates, including principles listed here addressing health and supporting flourishing ecosystems through regenerative development practices, as well as creating an environment in which diversity, equity, and inclusivity thrive. As well as, aspiring and recognizing adaptive and resilient built environments and decarbonizing to reflect the urgency of the climate crisis. All of these relate to heat issues. The rating system for existing buildings, so LEED version 5 for operations and maintenance, was the first to be released for version 5, and it made its debut last month at the 2023 Green Build Conference. It is available in draft form right now. And the rating system includes multiple credits with a focus on extreme heat and health, including a new site management policy credit in the SS category, or sustainable sites, the heat island reduction credit, and an occupant needs and health assessment prerequisites and mitigation credits. USGBC will offer LEED version 5 O&M in beta, and participants will work alongside USGBC as we implement the rating system, identifying opportunities for refinement and providing critical feedback that would help improve the O&M rating system, as well as the BD&C or new construction rating system that we'll be releasing next year. So your feedback is critical. So those interested in participating must complete an expression of interest by October 20th. So there's 2 days left. For more information on LEED version 5, please scan this QR code and it will take you to our webpage that will tell you more information. So thank you so much. I really appreciate the time, and thank you for your patience as I work through whatever is going on with my sinuses. So thank you so much.
Thank you, Karima. That's awesome. I really appreciate you powering through on this despite your illness. So thanks again for that. And we're really excited to watch the rollout of LEAD V5 and see how that goes. So now it is my great pleasure to introduce Shenyu Li. Shenyu is the assistant professor in the Department of Mechanical, Aerospace, and Biomedical Engineering at UT Knoxville. He received his PhD from Purdue University and was a postdoctoral associate at MIT. Shenyu's research focuses on using thermal sciences and materials innovation to enable high-performance thermal systems, including radiative cooling paints, thermal energy storage, and heat exchanger design for energy efficiency, along with solar desalination and water harvesting for water sustainability. His work on radiative cooling paints was awarded as World's Whitest Paint by Guinness World Records. So please join me in welcoming Shenyu.
Just want to make sure that slides is on. All right, hi everyone. It's a great pleasure to be able to present here. And today I will talk about the story and the journey behind our super white coating with a solar reflectance over 95%. And then the motivation is really the White House commitment to reduce carbon emission to reach net zero in 2050, which is an extremely challenging target. And among this carbon emission, one of the key contribution is actually the space cooling, where occupies almost 16% of the total electricity use and more than 113 million tons of CO2 emission. And if you look at, especially we just experienced the summer, and a lot of cases, it's actually the coating or the envelope of the housing or the urban heat island effect, where a lot of heat is just absorbed by the surface area. And sometimes that consists of more than 70% of total heat gain. And all this heat gain to provide a healthy and comfortable environment. We generally use conventional air conditioning that use electricity and to move the heat from indoor to outdoor. And this contribute a lot to the heat island effect to enhance or to increase the ambient temperature. And unfortunately, this downward cycle with hotter climate makes the air conditioning less efficient, so it consumes even more electricity. So that causes more carbon emission and global warming effect. So our goal is trying to find a way that minimize energy consumption while providing a good comfort building environment. And one of the very interesting concept is called radiative cooling. So radiative cooling is a passive cooling mechanism, so that actually everything on Earth is emitting a black body radiation. That's the thermal emission. So this energy is centered around 10 micrometers. And this is showing the spectrum or the intensity at about room temperature 300 Kelvin. But the atmosphere is actually not a closed system. There is a spectral window from 8 to 30 micron. So in that spectral window, which collide with our thermal emission, this radiation energy goes out of the Earth directly to the deep sky or the universe, which is about 3 Kelvin. So this outgoing heat flux consumes no energy, but it happens all the time. So we are trying to see whether this mechanism can give us a free air conditioning for buildings. And that's one, actually that was discovered way earlier, hundreds of years ago, when they actually pour water in a clear day in the desert area, and during the night it will cool the water down even to below 0 temperature and using that to make ice. So during the night, this is pretty easy to see during a clear sky where you have a certain heat flux just losing to the deep space. So the surface is cooling down by itself. But what's more important is we need cooling during the daytime when we have the solar sunlight coming to the surface. And there are UV, there's visible, and there are near infrared range based on the spectrum. But what our goal is, if we want to see this passive cooling mechanism to function and to provide some cooling, free air conditioning, what we need to do is reflect as much solar as possible. In one way, this reduces the heat gain. In other way, that we can see this cooling effect to be dominant in the process. And the easiest way is using some kind of paint or coating, where people have been trying in the academia world, that trying to see can we make the coating white enough that we can provide a full daytime cooling. So basically, the surface will stay below ambient or cooling itself throughout 24 hours. But people haven't seen that because you haven't reached the threshold of solar reflectance. That requires more than 90%. And if you look at the coating or the paint structure, it's the matrix material filled with different particles and fillers. The fillers are mainly has mainly the function to reflect this sunlight as much as we can. That's usually below 3 microns. The sky window emissivity that we're talking about radiant cooling, the way that you passive cool down the surface, is generally in the 8 to 13 micrometers. So based on this, we can actually co-optimize these two since they are quite different in the wavelength range. And we start with and kind of like commercially available mechanism using titanium oxide. And you can see this y-axis means how much light is absorbing. And this from 300 nanometer to about 3 micron. These are the solar spectrum. So here is all sunlight. And what we want is as low absorption as possible in this red or orange region. On the other side, around 10 micron, that's the atmosphere transparent window. That represents how much heat we can reject without any consuming energy. So we want this portion to be as high as possible. So generally, titanium oxide gives you a pretty good results. And you can see with the temperature, this is the purple line is the temperature throughout a little bit more than 2 days. And the green one is the ambient temperature. As you can see, we can make the paint most of the time is below the ambient temperature. It provides some cooling, that's good. But whenever there's more sunlight coming in, still the paint or the coating will be heated up, and that makes it again heating up and absorbing heat for that. So we're trying to figure out, can we push the limit a little bit harder? And one of the key points is we see this is not what we want in the ultraviolet region. So this may look titanium oxide paint may look white, but there are a significant portion, more than half of the portion of the sunlight is in the invisible range, either ultraviolet or the near infrared range. So not only we want to make the paint looks white, but also in the other region, we want to make it most reflective. And that comes back to how can we make a UV portion of the coating more reflective, and this helps with the longevity and UV degradation as well. So we look at different materials, we call the electron band gap. The higher electron band gap, you have a associated wavelength. That means anything below this wavelength, you're going to absorb. And there's nothing you can do with that because this is simply the material. So we choose, instead of using titanium oxide, which absorb anything below 400 nanometers, we are using calcite as one of them, and try to push it better. We just basically have a kind of like a hierarchical model where we are trying to look into when light is shining on one single particles, it will actually change directions. There's certain percentage the light will change directions. There's certain angle the light will go to another direction. And that's what we call scattering coefficient, absorption coefficient. And this function is really, phase function is where it's scattering. Is it going through, is it scattered back, or change a certain direction? So all these things combined together, you kind of have an effective medium. And using that, we can simulate what's the absorption, reflectance, and transmittance of a certain coating. And of course, with this model and validation, we can optimize and increase the volume concentration with calcite. For example, here we show that this is a solar spectrum. We show that with a higher concentration, we can reflect more and more light, up to 91%. And that these are all with single particle sizes. And as we continue to look into the fundamental physics, we found that actually single size, you may think that's maybe a good option to illustrate the fundamentals, but really in practice, it's actually very, very easy to have a non-uniform size distribution. And what we found out is this size distribution with a multiple particle size within the coating, we can actually further enhance the reflectance to 97%. And this really gave us confidence to do more experiment. We can see that the left one is the calcite paint we make. The middle one is the regular commercial titanium oxide. The right one is the black paint. We look at under SEM, we see that the particles are bonded together with some pores that's showing on that. So you see a rather matte finish on the coating. But the overall solar reflectance of the experimental data shows over 95.5%. And you may see like from 90 to 95, you may think, oh, that's only 5%. But actually, it means you reduce 50% of the heat gain. So any percent after 90% is actually a significant portion of that. So with that, we characterize the emissivity or absorptivity of that. That means how much light is absorbing. And what is good is we suppress the UV absorption that we think the titanium oxide has the disadvantage, where we have also the similar sky window emissivity. So overall, the coating is able to reflect 95.5% and still going to emit or lose energy 150 watt per meter square throughout the full day. And we did a quick demonstration really is to paint a P pattern with calcite paint we developed since at that time I was at Purdue, and then paint everything with a commercial white paint. So under regular camera, it's kind of tricky to see the actual pattern because both of them are appearing white. But if we put under the direct sun, because the higher reflectance, especially in the invisible range of the solar, the P pattern with our paint is staying a much cooler temperature compared with the regular commercial paint. And we measure that, like say the temperature of the calcite based on the solar, different solar at different throughout 2 days. We can see the paint always slow below the ambient temperature. So that's really demonstrate that the paint itself can cool itself down, and which is throughout the day, throughout 24 hours, and which is very impressive. And in fact, if you want the paint to stay the same temperature with the air that's flowing around it, you have to heat it up. So we actually did it. So we have to heat up the sample, and we have to heat up to about 30 to 70 watt per meter square Kelvin per meter square energy, so that the sample is going to be the same as the weather or the ambient temperature. And that also shows that a consistent cooling power that we can demonstrate with the coating. Similarly, we improved the coating using other materials, including barium sulfate, and we made a barium sulfate paint. You can see the accurate polymer is bonded the particles together, and again, this shows even better performance from the UV to the visible to the near infrared in the solar region, and we still maintain a very high emissivity in the atmospheric transmittance. And overall, we have 98.1% solar reflectance and high sky window emissivity close to 1. So you can see that, again, the temperature still stay below the ambient temperature throughout more than 1 day of operation, which translates to about 5 to 4.5 to 10 degrees C, or more than 110 watt per meter square cooling performance. So that's what gave us the opportunity and get us some publicity and rewarded with the whitest paint. And of course, as a coating, we want to make sure these are resilience and actually be able to survive the outdoor conditions. So we did try the abrasion cycles to see what's the abrasion resistance, which shows consistent results similar to other outdoor commercial paint. We put it outdoor for a few weeks to see the change on the solar reflectance. And you can basically use regular brush to brush it very similar to a commercial white paint, we show on the left. On the right is our barium sulfate acrylic paint, and we also did a little bit of brief water resistant test. You can see the water just ran down through clean. So overall, this gave us a lot of news. I think that's really because people are paying more attention, and we are seeing the urban heat island effect and getting really into our life. And the most practical way is really you see the electrical bills goes up, and we hope that our work can mitigate that problem and bring more energy efficiency buildings or environment to us. And thank you for your attention. This is my email. Feel free to contact me if you have any questions or ideas you want to work with. And I want to acknowledgement all the funding agencies for that. Thank you very much.
Thank you so much for your presentation. That was awesome information and very cool to see, especially at the end there. It looks like you've gotten some great media coverage on that. It's definitely, I know I've seen it, and many others have. It's been a story that got quite a bit of pickup from media, and definitely good to see the innovation with solar reflectivity. And so thank you again for your presentation. We've got a few minutes for some questions for both presenters. I've seen a few entered into the chat box, but feel free to add any others as well. I will go through and start with them. Karima's been kind enough to answer a couple in the chat box already, but if she wouldn't mind, for those not into the chat box, would you mind, Karima, answering the first one about lead points being applicable to cool pavements, just for those that haven't seen the chat?
Yeah, no problem. So the first question was, are lead points also applicable to cool pavements? So yes, to earn the 2 points in the credits, you can project teams can choose non-roof measures and use any combination of non-roof or roof measures or parking undercover. So examples of non-roof measures include cool pavements or using paving materials with a higher solar reflectance value or using an open grid pavement system. The second question I thought I responded to was, how would reflecting heat from buildings not just make the area surrounding the buildings or pavement hotter? So when solar radiation is reflected by surfaces with high albedo values, such as cool roofs and walls and reflected pavements, the heat associated with that radiation is redirected away from the surface, so it doesn't get absorbed by the material, and so that way it doesn't contribute to the heating of immediate surroundings, and instead that heat is reflected and dissipates into the atmosphere. So some of it might be absorbed by the atmosphere, but the net effect is a reduction in the amount of heat retained by the surface, leading to lower surface temperatures and cooler environment in the vicinity of those materials. So that's how that works, and it shows how materials can really help by mitigate the heat island effect by preventing the buildup of that excess heat. So it really is about albedo effect, and also what we mentioned earlier, by keeping buildings roofs cooler and pavement cooler, you could reduce the need for air conditioning. Less energy consumption means fewer greenhouse gas and lower heat generation from HVAC. So that also contributes to the net cooling effect, as well as shade creation. So when reflective surfaces are used, they could also be used as shade, and they can help create cooler and shadier microclimates around the building or the pavement. So thank you for your questions.
Thank you for the detailed answers to those. That is very much appreciated. I will add on the second one, There's things you can do as well with how you're reflecting and what you are reflecting. Like with CoolSeal, we're using infrared reflective pigmentation to fluoresce UV into infrared so that we're minimizing the amount of UV reflectivity, especially if it's a surface where someone's walking on and that sort of thing from a human health perspective, to mitigate those things as well through fluorescing UV into infrared, making it healthier um, for those that are walking on those surfaces and for anybody in that environment. One of the questions was, how often would CoolSeal need to be applied to maintain reflectivity of roadways? CoolSeal lasts about 5 to 7 years on average. It's 2-coat application, and then after that time period, it would be reapplied. And not always do you need a 2-coat application on the following. There may still be some pavement down that you just may need a refresher 1-coat for that. So thank you for your question there. And then one of the questions we had for Jean Yu is, with calcium carbonate paint, do you mean that you're only painting with calcium carbonate and not with TiO2?
In that works, yes, just with calcium carbonate. We did not put titanium oxide there, most because titanium oxide absorb the UV side. So once you have some of them, when you have a certain amount, you're going to absorb the UV side, UV light. Not that it's the end of day, because in that work we are really trying to push the limit. So that's why we are only using the calcite. Yeah.
Awesome. And then the next question just came in was asking about using of primers to help maintain the color and avoid dirt pickup. Is there anything to that effect to try to avoid some dirt and debris and that sort of thing?
Yeah, that's actually a very good question. I mean, primer, it's if it's better helps with coating some surfaces, definitely, because that's below the, for example, if it's below the white surface, it doesn't really matter. Another thing is the picking up a dirt. That's a good concern, especially with more matte finish coating. That's kind of the direction we are working on, is trying to make sure that we have a variety of surface finish you can get, especially a little bit more on the glossy side, so you can avoid some dirt. Theoretically, yes, if you somehow pick up dirt, it got dirty, it got darker. You put some dirt, that yes, they will be affecting some of those. But good thing about if we are making the coating as shown in the running test a little bit hydrophobic, so all the during water will help us, especially a wall or a sloped roof. That will help self clean up some portion of that. Yeah.
Yeah, absolutely. That's great to hear about the innovations there. It's something that we're undertaking with CoolSeal as well, making the product hydrophobic and obviously trying to make it adaptive to when rain and things occur. To that, we've noticed that it helps to clean it up thoroughly. And unfortunately, there are some parts of the world that don't get a lot of rain, so we have to adapt in other ways. And that's where we've taken on things where we've added infrared pigment to darken it. So that from an aesthetic standpoint, from a roadway surface, that you're making it more appealing, and we're trying to color match the tire marks and those sort of things. So definitely many things you can do there as well to offset those things. And then the next question was asking about, does CoolSeal preserve the pavement and how? So CoolSeal is an asphalt maintenance product first and foremost. It's designed to extend the life of asphalt by coating the surface, protecting it, the asphalt from the sun, and as well as from water penetration and those sort of things. So by coating the surface, you're allowing it to keep its flexibility, avoid it from being cracked and becoming brittle. The sun does a pretty good job of beating up asphalt surfaces, and so by coating it, we are helping to reduce that impact of the sun. And also by using the solar reflectivity also helps to dampen that effect as well, because with the traditional black asphalt coating, you are absorbing most of that heat, and that coating is taking a lot of the punishment. With the reflectivity, you're able to reflect that heat and also make it so that that coating doesn't have to work as hard to combat that subsurface from being dried up. And then also just due to that, you're seeing full depth cooling as well. So less expansion and contraction of that asphalt due to it not heating up and cooling as much. So you're seeing an extension of life there. And then the water protection, just the coating protecting it from, asphalt can absorb a lot of water and can get into and penetrate and cause a lot of subgrade issues and those sort of things. So the coating helps to prevent water from wreaking havoc as well, to the surface. In addition, and then another question was if CoolSeal is effective if there's enough tree canopy over the pavement surface. So one of the things that we're seeing a lot of with cities is, kind of a holistic cooling approach where they're looking to target urban heat island mitigation through multiple tactics, as we've learned about today, that there's not only, one solution that fits all. So a lot of cities are implementing as much of those things as possible to cool things down. And, a lot of studies have shown that tree canopy and shade have been one of the most effective, if not the most effective, to heat island mitigation just due to shade. But there are definitely some roadblocks to that in terms of, ability to plant trees, keeping trees alive, also developing of canopy. So a lot of cities are planting trees alongside with cool pavement, and that tree canopy may take 10 to 20 years or so to develop to where it's providing shade. So things like cool pavement, cool walls can help bridge the gap while that canopy is developing. And then once that canopy is fully developed, there may not be as much of a need for cool pavement at that time. But while that shade is still taking place, it definitely provides that immediate impact while tree canopy is growing. And then in certain areas like the Southwest, where you can't really grow a certain amount of trees that are going to provide tree canopy, it's just not an option for some people. So in those instances, it's going to be more beneficial. But yes, tree canopy is something that is great, and kind of bridging that gap is a great approach we've seen a lot of cities use as well. And so I know we are right about 2 o'clock here. Want to once again say thank you to both of our presenters today for speaking. Was great information and really informative, and got some more information for you here on the slide. We will be sending out this recording via email, and we will also make the slides available for all of you to see, and encourage you to reach out to all of us with any additional questions offline, and look forward to seeing you all on another webinar this winter. So be on the lookout for that, and I'll let Maria wrap us up here.
All right. Thanks again to the awesome speakers, Shenyu and Karima. Thank you so much. I'll pat myself on the back. Karima's examples of the projects in Louisville, Kentucky were the ones I started when I was sustainability director, and launched those programs for heat mitigation. But anyway, please join us and be on the lookout. Reach out to us for any questions or if you need assistance with your projects, and we will look forward to seeing you on our next webinar. Thanks again.
Thank you. Have a good day.